Good morning. This is the first video for AP Calc section 6.2. We are talking about solids of revolution. So you'll recall in section 6.1 we were finding the area between two curves. Now we're going to take a region between a couple of curves and we're actually going to revolve it around an axis in order to create a three-dimensional figure. We're going to be finding the volume of that. And there's really three different methods we're going to use, or three different types of solids you'll be asked to find the volume of. This video will be just the first of those three. Okay, so let's look at an example. It says, let R be the region bound by, and I have three equations, y equals 1/2 x, y equals 0, and x equals 8. It says, find the volume of the solid formed by revolving R around the x-axis. So let's make a sketch, and I should apologize because I don't draw very well, especially trying to draw three-dimensional, but I'm going to try. So 1/2 x is just a line, looks like that. Slope is 1/2, up 1/2. And y equals 0 is the x-axis, and x equals 8 we'll put about there. We'll call that 8. So happens to be a triangle. If I were to revolve that region around the x-axis, it would come out from the screen and then go into the screen. I'm going to try and put a dotted line here for what it would look like if I revolved it. And I might put a little circle there, try and make it look three-dimensional. It turns out that it would be a cone. This particular shape would be a cone. And just like when we used integrals to find areas, we started with shapes, and we can find the area under a curve if it happens to be a shape. We know the area. Same thing here. There's a geometry folder. There's a geometry formula that you may or may not remember for the volume of a cone. Tell you what, let's do that first. Let's use geometry, and of course, the goal here is to not need to use geometry and to use calculus when we can't use geometry. But the volume of a cone, you may or may not remember, is 1/3 pi r squared h. So that right there is the point 8, 4. So in this, using geometry, at least for the moment, the volume of this would be 1/3 times pi times r. The radius goes from there to there. The radius of the base of that cone is 4. So that's 4 squared. And then the height of this cone goes from there. The height of that cone would be 8. So if I did that, I think it turns out to be 1628 pi over 3. Now that's using geometry to find the volume of a cone. I want to now show you how we can use calculus to do the same thing. So I'm going to go to new screen here. I'm going to put this picture back. Looks like this, and like this, and like this, and like this. And then when I revolve it, it looks like this. Okay, so I'm going to take a typical cross-section rectangle. And remember, when we were finding area, the concept of an integral was, first we approximated area with rectangles, and then we said, what if I could have an infinite number of rectangles, each infinitely skinny? And when you integrate from a to b, you take the integral from a to b of f of x dx and find the area under the curve. That really is essentially finding the sum of the areas of an infinite number of rectangles that are each infinitely skinny. Well, the same concept here. If I take that blue rectangle and I rotate just a rectangle around the x-axis, that looks like that. It's a three-dimensional. It's a disc. It's a cylinder. Think of it as a coin, if you will. So the cross section is a disc, and actually, we're talking. The book calls this the disc method, and for today, it's the only method we know. But when the cross section, a three-dimensional cross section, is in fact a disc, well, obviously there would be a smaller. There'd be a disc there, and there'd be a disc there, and there'd be a disc there. Obviously, the dimensions change as I go from beginning to end here. But if I could, instead of finding the volume of one disc, if I could find the volume of an infinite number of discs, each infinitely skinny, and the integration process does that for us. So I'm going to write the one disc, the volume of a disc, that's just a cylinder, is pi r squared h. That's the formula for the volume of a cylinder. Each disc is really a little cylinder kind of turned sideways. So what we're able to do here is by integrating this, from A to B. Now, what are A and B in this case? Well, think of all these disks lined up. They go from x equals 0 to x equals 8, because that is the point based on the problem. That's the line x equals 8. So it's the integral from 0 to 8, and it's pi r squared h. Well, remember, pi is just a number. I'm immediately going to put the pi out here. That's just a constant. Now, h, again, let's look at, I'm just looking at this one typical cross-sectional disk. The height of that disk is this distance, like right there. It's the thickness of a disk, and that's just my dx. That's my change in x, which again, ideally is getting smaller and smaller as these disks get skinnier and skinnier. But the height of the disk is just dx. And the radius goes from here to there. I'm labeling it in green. I'll just like this distance right here. That's supposed to be some kind of bracket. Didn't do that well. That's the radius. Now, it is true that clearly for each of those blue disks that I've drawn, as they change inside, the radius changes. So it's not just a number, but this function right here, as I'm going to make bolder in red, that's the line y equals 1/2 x. I'm going to label that's the line y equals 1/2 x in this particular problem. And that green radius is, in fact, the y value of the function. Like whether I drew it or I draw it like there's, that's supposed to be green. There's a radius there. There's a radius there. There's a radius there. All of those radiuses are the y, since they go from 0 up to the function, whatever the y value is. Like this point right here, that's just some random point x comma y on that function y equals 1/2 x, and that distance r is the y value. So in this case, the radius is just the y value, which is just 1/2 x. And this is kind of the simplest case, if the region is up against the x-axis and you're revolving it around the x-axis, then the radius is going to be the y value of the function. It won't always be the case, but it often is the case. So my r squared in this formula is 1/2 x squared. So I want you to recognize, or hopefully acknowledge, that this formula, which is just a formula for the volume of one disk, turned into this integral, where by integrating it from 0 to 8, I am adding up I'm finding the sum of the volumes of an infinite number of disks that are infinitely skinny. So once I get it to there, now it's an integral I can take. So now I will scroll down here. This becomes pi times integral from 0 to 8. Let's see, 1/2 x times itself would be what, 1/4 x squared dx. Again, I haven't taken the integral yet. Now let's take the antiderivative. That's pi times, let's see, x squared would be, so that's 1/4. The integral of x squared is x to the third over 3. That from 0 to 8. Again, this part of the process shouldn't be new. I might clean that up to be, let's see, 1/4, and there's a 3 in the bottom. I might call that pi over 12 at the moment, because that's just numbers. And now I'm going to plug it in. So I've got 8 cubed minus 0 cubed. 0 cubed is obviously 0. 8 cubed turns out to be 512. You may have to calculate that, but I happen to know it. 512 pi over 12. And if I divide top and bottom by 4, that fraction does reduce. Turns out to be 128 pi over 3, which is what we got when we used geometry to find that volume. So again, what's new here is being able to recognize that the cross section is a disk. I'm adding disks, the volume of disks, and the thickness of each disk is dx. Now, if I start stacking disks this way, which I will do in one problem here, then the thickness would be dy. So be aware of that. But at the moment, the thickness is dx. And then the radius here was the y value of the function. Okay. That example, we could have used geometry because it happened to be a cone, and we happen to have a formula for that. Now let's look at one where we can't use geometry. Well, other than that, it's very similar. Okay, next example. Let R be the region bound by y equals root x, y equals 0, and x equals 4. So again, I'm going to draw a picture here. Root x kind of looks like this. It's kind of a sideways parabola. We'll call this 4. The y equals 0 is the x-axis. So we're taking that region, we're still revolving it around the x-axis. So that look like it revolve around. It kind of looks like a bowl, kind of. We're trying to make this look three-dimensional, which I don't do very well. So again, I have one typical rectangle, which when I rotate that rectangle around the axis, I get one typical cross-sectional three-dimensional disk, and that is a disk. Again, I don't have to draw others, but if I had a rectangle there or there or there, again, I'd have disks corresponding to those as well. So since my cross section is a disk, I'm still starting with the formula V equals pi r squared h. That's the formula for the volume of the disk. But in this case, let me get a little space here. Let me get an eraser going. Let me get a little space there. This would be my pi comes out front. Integral from A to B. Again, I'm summing up these disks from x equals 0 to x equals 4. So from 0 to 4. And the radius, well, the radius goes from the x-axis up to the curve. That distance right there is r. And that, again, because the radius is going from the x-axis, which is 0, up to the curve, that's the y value of the function. Whatever the y value is of the function, that's the radius. So the radius here is just y, which is root x. So there's r squared, and then the height, the thickness of one disk is still that change in x, that dx. Just like with u substitution, once you get to the integral, sometimes the integral itself is not that difficult. So now let's finish it from here. This is pi times the integral from 0 to 4. Conveniently, root x squared is just x. So that's just pi times, what's that, x squared over 2. That is the antiderivative of x. And that's from 0 to 4. And that's, again, I might pull the pi over 2 out. And then just do 4 squared minus 0 squared. What's that, 16 pi over 2, which is in fact 8 pi. That is the volume of that solid of revolution. So there's another example where the radius was just the y value and the cross section was a disk. So those two examples, other than changing the function inside from 1/2 x or root x, was the same process. Okay, two other examples to show you, and they both do something different. One of them stacks points vertically, and the other one, this next one, the line we're rotating around is not the x-axis, it's just a different line. So let R be the region bound by y equals 2 minus x squared and y equals 1. Find the volume of the solid form by revolving R around the line y equals 1. So let's sketch this. Let's see, 2 minus x squared looks something like this, where that would be 2. And y equals 1 is just this line right here. So there's my region. So actually, I'm going to erase, I don't need that part of this function just because of the constraints of this problem. So there's the region bound by that parabola, 2 minus x squared, and y equals 1. And you'll notice I am revolving this around the line y equals 1. So this dotted line here, it's not a line. This dotted line here is my axis of revolution. I'm revolving that region around that line. So it would look like this. Almost looks like a football, for lack of a better, it wouldn't need to have a name for it. So here is a cross-sectional rectangle in my original region. And when I rotate that region around the line y equals 1, here's the bottom half of this thing. So my cross-section is still a disk. So I'm still adding up the volume of lots of individually infinitely small or skinny disks. So I'm still starting with the formula V equals pi r squared h. And so some of this I can immediately follow the other process. So the pi comes out here, but we'll worry about A and B in a moment, and we'll worry about the radius in a moment. H is still the dx. That's still the thickness of a disk. Now, as far as integrating it from something to something, the first example, one was 0 to 8, and the second one was 0 to 4, and the equations kind of gave you those numbers. This one doesn't give you those numbers. So I'll put these in blue here. Like these two blue dots right there. I'll erase some of this. I need some space down here. I need to know what x values those blue dots. Like I have a bunch of disks that go from x equals I'm not sure what up to x equals I'm not sure what. And we saw this back in the last section. If you don't know where two equations intersect, just set them equal. So these two equations up here, I can set them equal and solve it for x. I need to do that to find a and b. So if I set 2 minus x squared equal to 1, and I add the x squared over there, and I subtract the 1 over there, and I square root. Turns out to be the square root of 1 is a plus or minus 1. Square root of 1, right? I just square rooted that and square rooted that. So it turns out these two x values are at x equals -1 and x equals 1. The problem didn't tell us that. We needed to figure that out. So that's where my a and my b come from -1 to 1. So that's the first one thing different about this problem is that we kind of had to figure out a and b. But next, let's talk about the radius. So I'm going to color it in purple. Here's the radius. It doesn't go from the x-axis up to the curve. It just goes from the axis of revolution, which is line y going up to the curve. So this purple distance is r. So we got to figure out what r equals. Well, the first two examples, the radius was the y value of the function. If I were to highlight, let me get a skinny highlight, from there down to there, like from 0 up to like that yellow highlighted line, that's the y value of the function, but that's too big. My radius is less than that by how much? Well, this distance down, I meant to change colors. This distance down there is 1. So it's the y value of the function, which was that yellow, minus 1, because my axis of revolution was 1 unit up. So whatever the y value of the function is, and obviously that changes as I go throughout this football shape thing. Like for instance, if I draw over here like this, let me go back to pen here. Let me draw a purple radius over here. So this radius right there, if the question, what's that radius? Well, the y value of the function goes from 0 up to there, but that's 1 too big. It's too big by 1 because it's from 0 to 1 is not in the radius. So it's going to be the y value minus 1 in this case. So my r is the y value minus 1. But of course, what was my y value? My y value is 2 minus x squared, that's just 2, minus 1. So here you had to figure out that the radius was the y value of the function subtracted by 1. So I clean that up, 2 minus x squared minus 1, I think 1 minus x squared. So there is my radius. So if you're not revolving it around the x-axis, you have to pay more attention than usual to calculating what is the radius. So now here in my formula, this is now r squared, so 1 minus x squared squared. There is the integral I'll need to take. Let me throw this out there on think of it. Sometimes, either on my test or on the AP test, if the functions were weird enough, it might say just set up, but don't evaluate the integral. Like if this was a crazy function that we didn't know how to take the antiderivative of, it might just ask us to set up the integral. This one we can in fact solve. So I'm going to just rewrite this again. This is volume equals pi times integral from -1 to 1 of 1 minus x squared dx. Make sure I typed it in correctly. -1 to 1 minus x squared. Okay, so now you need to remember that before I take the antiderivative, I'm going to multiply that by itself so that, again, I'm writing it like this. I might do this in my head, but I'm distributing this. I want to write it out. I want to expand it. So that's just 1 minus x squared minus 2x squared, and then plus x to the 4th dx. Now I can take the antiderivative. So that is what, x minus 2x cubed over 3 plus x to the 5th over 5, evaluate from -1 to 1. And now I just need to carefully evaluate it at 1 minus evaluate it at -1. And again, I'll leave the pi way out here. If I evaluate this at 1, I get 1 minus 2/3 plus 1/5. And if I evaluate it at -1, I get -1 minus, let's see, -1 minus -2, so plus 2/3, and then minus 1/5. In the interest of time, I'm gonna quickly we'd have to make 15ths out of all that, which you all could do. I'm gonna save us the time. This turns out to be 8/15 minus -8/15, which turns out to be 16 pi over 15. That's the volume of that solid of revolution. Okay, one more example. And this example, you'll notice, I'm revolving something around a vertical line. So the disks that I'm stacking are kind of on top of each other. So let the region bound by y equals root x, x equals 0, y equals 2. Let me draw that region. Y equals root x looks like that. X equals 0 is the y-axis, and y equals 2. There's 1, 2. So this is y equals root x. So like that right there would be the point 4, comma 2. There's my region, and I'm rotating it around the y-axis. So now it's going to look like, again, I don't draw anything very well here. It looks kind of like that. And if I rotate this around, it kind of looks like that. It almost looks like I don't know, like almost like a trombone, the bellow of a trombone. I'm not sure what shape that is, a bowl that kind of shapes out. Anyway, but my typical rectangle now looks like this, which when I revolve that around the y-axis is over here. Notice that cross section three-dimensionally is still a disk. It's still a cylinder. And since my cross section is a disk, I am still dealing with the formula V equals pi r squared h. That hasn't changed. But let's figure out what does change. Talk to me about, you're just watching a video. Let me talk to you about h. H is the height of a typical disk. It's the thickness of the cylinder. Before, the disks looked like this, and so I said my height was the thickness, which was dx. Now I've turned this way, so it's the change in y. So my height is now dy, not, didn't mean to do that, dy, not dx. And as far as my a and my b, so this would make that down there. So it's going to be e equals pi times integral from something to something. Now let's be careful with that something to something. I have one disk drawn. If I draw another rectangle here, and I'll draw one more out here, that when I rotate them become that and that. My disks are on top of each other, so I am summing up disks that go from y equals 0 up to y equals 2. So now it's the y values that, like everything from y equals 0 to y equals 2. Don't go from 0 to 4 with x's because I'm stacking them this way, so the y's go from 0 to 2. This is from 0 to 2. I've got my dy here. Now let's talk about the radius. I'll tell you what, I'm going to erase my biggest. Let's see, can I erase that? Crap, that's not going to work. That's not going to work. Oh no, I went the wrong way. Okay. Let me erase this. I'm trying to erase that. Okay. So my radius, I'm trying to squeeze a radius right in here. That green line right there is my radius. And again, here, right here, this point is some point x comma y on that function. That radius is the x coordinate. Starts at 0, goes to the x. So whatever the x coordinate is, that is the radius. So the radius is x. I don't want to put x in here because I'm doing this whole thing in terms of y. So I want to know what that is in terms of y. So notice this function up here, y equals root x. I may need to solve that for x. And obviously, if I just square both sides, this becomes y squared equals x. So the x coordinate is my radius, but I need it in terms of y. So that turned out to be y squared pi r squared h. So that's, as you rewrite these integrals, be aware that you're just rewriting the formula pi r squared h. Pi goes out front. H is the thickness, which here is dy. We've got to be real careful finding the radius, which we just did there. Okay, so now we can finish this. This is pi times integral from 0 to 2. What's that? Y to the 4th dy. And that's just pi times y to the 5th over 5, which is pi times 2 to the 5th over 5 minus 0 to the 5th over 5. And 2 to the 5th is what, 2, 4, 8, 16, 32. So I think it's 32 pi over 5 is the volume of that solid. So there's 4 examples of finding volumes of solids of revolution. And so far, the cross-section is a disk. Think of it as a coin, a cylinder. In the live lesson on Wednesday, we'll start seeing where the cross-section is something different, but not yet. So the assignment is on page 425. And you got 1 to 4, and you got 7 to 10, and you got 13B and 13C. I'm picking and choosing here for ones that still have disks, and then 14B and 14D. So that's all I've got. Enjoy your Tuesday.